Imagine a universe that seems calm and predictable, where galaxies drift apart at a steady pace. For nearly a century, astronomers believed they had measured that expansion well enough to build a complete history of the cosmos. But now stunning observations from the James Webb Space Telescope, our most advanced eye on the sky, are throwing those assumptions into question. Launched in late 2021 and fully operational by mid-2022, James Webb is designed to peer deeper into space and further back in time than any instrument before it. What it has found is shaking the very foundations of cosmology, from galaxies that appear impossibly massive and mature only a few 100 million years after the Big Bang to unexpected patterns in how the universe's expansion is measured. These results are forcing scientists to revisit the core of the so-called standard model of cosmology. Could it be that the universe is not expanding the way we thought? Could our timeline of cosmic history be wrong? To grasp the magnitude of these new findings, we first need to understand the foundation of modern cosmology. For decades, astronomers have relied on the lambda-cold dark matter model, LCDM for short. In this framework, the universe began 13.8 billion years ago with the Big Bang, followed by rapid inflation, and has been expanding ever since. Galaxies recede from each other at speeds proportional to their distance, a relationship first discovered by Edwin Hubble and expressed as the Hubble constant. This model assumes that about 68% of the universe is dark energy, an unknown force driving accelerated expansion. Another 27% is dark matter, which holds galaxies together, the ordinary matter that makes up stars, planets, and people accounts for less than 5%. Until recently, most observations from the cosmic microwave background to galaxy clustering fit this model remarkably well. The universe's expansion seemed smooth and predictable. Yet, even before the James Webb Telescope, small cracks were showing. Astronomers measuring the Hubble constant in different ways using the early universe's light versus nearby supernovae kept getting slightly different answers. This discrepancy, known as the Hubble tension, hinted that our picture might be incomplete. Now, with Webb's ability to see galaxies from the universe's first few 100 million years, those cracks have widened dramatically. To test and refine cosmological theories, scientists need to look back in time. Literally, the farther we look into space, the older the light we see. The Hubble Space Telescope took us billions of years back, but it had limits, especially in the infrared range where the earliest galaxies shine. The James Webb Space Telescope, JWST, launched in late 2021, was built to break through those limits. With a 6.5 meter primary mirror, more than 2.5 times larger than Hubble's, and detectors optimized for infrared light, JWST can capture faint signals from galaxies formed only a few 100 million years after the Big Bang. Within its first months of operation, JWST began to deliver breathtaking deep-field images that stunned both the scientific community and the public. Galaxies that had previously appeared as mere smudges now resolved into intricate spirals and clusters. But along with these beautiful pictures came a startling surprise. Some of these galaxies were far more massive, dense, and mature than any model of early universe evolution had predicted. These observations quickly became headline news. If such massive galaxies existed so soon after the Big Bang, then our timeline for how quickly stars and galaxies form might be fundamentally wrong. The JWST was not just adding detail to known theories, it was forcing a rewrite. Among JWST's most astonishing findings are galaxies with masses comparable to or exceeding that of the Milky Way. Yet these galaxies appear only 200 to 300 million years after the Big Bang. In standard cosmology, there simply shouldn't have been enough time for such structures to form. These young but massive galaxies are packed with stars and display surprisingly mature chemical compositions, including elements like carbon, oxygen, and iron that normally require multiple generations of stellar life cycles to accumulate. Theories of slow, hierarchical galaxy formation, where small clumps of matter merge over billions of years, cannot easily account for these observations. Some astrophysicists propose that star formation in the early universe was far more efficient than previously thought. Others suggest new physics, perhaps dark matter behaved differently in the past, or perhaps our understanding of how quickly gas cools and collapses into stars needs revision. Adding to the puzzle, JWST has identified compact, bright objects that may represent an entirely new class of ultra-dense galaxies or even direct, collapsed black holes forming with unprecedented speed. Each possibility challenges core assumptions about cosmic evolution. The unexpected discovery of massive, well-formed galaxies so soon after the Big Bang forces scientists to rethink how cosmic structures evolve. Traditional theory assumes galaxies form hierarchically, tiny clumps of matter slowly merging over billions of years. But JWST's data suggests something else. Either the earliest galaxies formed stars far more efficiently than predicted, or entirely new physics is at play. Perhaps dark matter cooled and clumped faster than we thought. Perhaps the very rules of gravity, as described by general relativity, need subtle revision. Some theorists are exploring cold dark matter plus early feedback models where primordial gas collapses rapidly under intense pressure. Others consider exotic possibilities such as variations in the fine structure constant or interactions between dark matter and dark energy that could accelerate growth. Each scenario, if confirmed, would ripple across every branch of astrophysics, from how black holes form to how elements heavier than hydrogen are distributed. Even before JWST, astronomers faced a troubling inconsistency known as the Hubble tension. Two main methods give conflicting numbers for the universe's expansion rate. Measurements based on the cosmic microwave background, the afterglow of the Big Bang, predict a lower rate. Local measurements using Cepheid variables and supernovae show a higher rate. JWST now adds a new twist. By observing the very earliest galaxies and refining distance measurements, Webb provides independent checks, and they tend to confirm that the tension is real, not just a calibration error. If the Hubble constant truly varies depending on how and when it's measured, something profound is happening. Perhaps dark energy's influence has changed over time. Perhaps unknown particles or forces altered the early universe's dynamics. Either way, the most basic number describing cosmic expansion may no longer be a constant. If the universe's expansion is more complex than we believed, what does that mean for its ultimate fate? Classic scenarios include heat death, big freeze, expansion accelerates forever until galaxies drift apart into darkness, big crunch, expansion eventually reverses and the universe collapses. Big rip, dark energy grows so strong that even atoms are torn apart. A non-uniform or evolving expansion could open other possibilities. It might mean phases of acceleration and slowdown, or unexpected transitions billions of years from now. These are not just abstract speculations. Understanding the true expansion history affects how we model dark energy, the birth of stars, and even the potential habitability of galaxies. The James Webb Space Telescope was built to illuminate the universe's first light. Instead, it has illuminated our ignorance. By revealing galaxies that are too big, too old, and too organized for standard theory, JWST has forced scientists to revisit the very framework of cosmology. Whether the solution lies in faster star formation, exotic dark matter, or entirely new physics, one thing is clear. The universe is not expanding the way we thought. Our cosmic history, and perhaps our cosmic destiny, must be rewritten. This is the essence of science. Each discovery opens deeper questions. The universe, it seems, still holds secrets far stranger than we can imagine.